Hi guys, so my name is Jessica and my partner is Christian, and we'll be going over the synthesis of Aprovel, also known as Irbesartan. So to start things off, the table of context will go into the background, synthesis, mechanism, future work, and then references. So to start off, what is Aprovel? Well, the generic name is Irbesartan. Aprovel is actually, or also known as Irbesartan, is a common cardiovascular medication. So this prescription is used for high blood pressure, also known as hypertension, and type 2 diabetes. So we'll kind of dive into a little bit of some bio and then kind of pop out of it into history. So the bio part of it is that this medication is an ARB, which is also known as an angiotensin II receptor antagonist. That's a long-filled word, so we'll just call it an ARB. And that's what is common with cardiovascular disease medications. So this blocks the angiotensin II hormone that we have, which then, when you have high blood pressure, then it allows for the blood vessels to relax and then to get rid of that extra salt and the water in the blood, allowing for lower blood pressure and thus better kidney function. So this is just the basis of how an ARB works, which in this case, Aprovel does just that. So then to kind of pop out of that bio, we're going to go into the history where it was patented in 1990 and it was approved for medical use in 1997 by Sanofi. And the picture at the bottom left kind of shows you what this drug medication looks like, and it gives you a good gist of, it checking the blood pressure. So then oh, look, I'm back in a good range, yay.
Synthesis of a Aprovel consists of four major parts. First, the reaction of the acid chloride using the amine here, and then which then forms the amide in this particular portion, and then using the amino ethyl molecule here, reacts and attaches itself, and then this attachment then reacts with trifluoroacetic acid to form a ring under this first carbonyl, and then finally, using sodium azide and tributyl tin chloride, it forms a tetrazole at this bottom portion in the cyanide portion of the molecule. Starting off with steps 1 and 2 of the mechanism, first the amine attacks the acid chloride. From the acid chloride, the chlorine gets kicked off and reforms the carbonyl, and then a base deprotonates the nitrogen portion and takes away a hydrogen. And then from there, a base then deprotonates the carboxylic acid from this portion. And then from there, this oxygen anion attacks another section of the acid chloride. And then as we see here, then the chlorine gets kicked off to form an anhydride, which then we are able to use the other part needed to form the Aprovel during the next few steps, using the small nucleophilic amino ethyl portion, and then attacks this carbonyl. And then as we see here, as we formed a leaving group in the previous steps, now we are able to kick off the small leaving group, which then from there, as we go on and proceed from step 3, we are able to deprotonate a hydrogen from this nitrogen group. And then from there on, we're able to proceed with trifluoroacetic acid and protonate this oxygen. From there, we are able to proceed with a intramolecular reaction, which then moves the pair of the electrons onto the oxygen to remove that positive charge. From removing that positive charge, we are able to use that trifluoroacetic anion and then deprotonate this nitrogen group and to remove this positive charge. And then from there on, we're able to protonate this and prepare a leaving group. And as we form water, we're able to kick it off. And then nitrogen uses its electron pair to form a double bond to be able to kick off this water. And then from that water, we're able to use the trifluoroacetic anion and then deprotonate this and send back an electron pair back to nitrogen, which then completes this part of step 3. Going on with step 4 of the mechanism, we have sodium azide attacking the tributyl tin chloride, and then the chlorine in the tributyl tin chloride leaves, following on the electron pair being sent back to this nitrogen of the azide group. And this part is crucial to be able to set up the following reactions in the mechanism with the cyano group. And as we see here, salt is a byproduct, but we also have to recognize that typically in a salt reaction, radicals are used to be able to illustrate the mechanism, but due to the simple nature and for it being a single chloride, we'll just use the fact that the electrons are being sent back to this nitrogen, and then the sodium being positively charged is then being attacked with the chlorine, negatively charged chlorine, to be able to create this salt here. Following along with this that we prepared in the previous steps, we have this negatively charged nitrogen. So I'm going to attack this carbon, this triple bonded carbon, and then as we see here, one of the triple bonds of this cyano group attacks the tin, and an electron pair is sent back into this nitrogen to then be able to attach this azide group and then send the tributyl tin onto this other fourth nitrogen.
Okay, so I'm back again, and I'll finish up this last part of the mechanism. So I almost said hydrogen. Water. So this oxygen has a lot of lone pairs, and it's like, hey, look, I can donate some. So what's going to happen is that in turn, it's going to move to this SN, which is this tin, which then the next part of this then is that then oxygen is like, hey, look, I just lost some electrons. I'm kind of sad. So he's going to show right here this like positive charge. And then what's going to happen is that SN is like, hey, look, I just got some electrons. I'm a little full. So it's going to be represented as this minus charge, which then happens is that this molecule is like, hey, look, I want to attach, and it's going to attach right here to this nitrogen and in between this carbon right here. So then what's going to happen is that this carbon right here, I'm talking about right here, is like, hey, look, I got a lot of bonding. So in turn, then it's going to kick off and make this double bond into then a single bond, and then what's going to happen is that these electrons will then become a lone pair, which is then right down here, if you can kind of see it, I'll put it in a yellow highlighter. So right here, that's represented with the lone pairs, and then it's also like, hey, look, I'm full with electrons, and it has then a minus charge, which then, let me switch over to my pen. This is like, hey, look, I got some electrons. Hey, this acid right here, the hydrogen part of it is like, hey, look, I can accept some electrons, so it's all happy. So the nitrogen's like, you're more than welcome. So then it's going to attach over here. Excuse my arrows, I'm on my computer. So then what's then going to happen is that this is then going to result in the nitrogen and the hydrogen bonding together, and the A in this will then just be like, oh, I'm all sad. So it's going to disappear. So not really, it's not going to disappear. It's still going to be in the solution, but it's just not going to be attached in this molecule, which then results in our final desired product. So that's really exciting. So to go into the future work, since Irbesartan, also known as Aprovel, kind of pick your poison, you can just say whatever you want, Irbesartan or Aprovel. So it preserves kidney function, which other ARBs, right, so those are the angiotensin II receptor antagonists, the long-filled word, may be involved to manage other diabetes complications. So other ARBs are also like, other cardiovascular medications. So since it does preserve kidney function, why not investigate if it can help more than one thing in diabetes? Then the further research into cardiac metabolism and the effects these medications hold on the heart. I think that would be pretty cool, because in the papers they didn't really mention like how it affected the heart. So kind of understanding like, hey, look, what is it actually doing in the heart? Is it helping the heart in the long run? Kind of thinking instead of this short-term effect of it relaxing those blood vessels so that then you can lower the blood pressure, like what if it's the long-term effects is actually hurting the heart? So kind of looking into that a little bit more. They give you like a brief, kind of telling you, oh, this, won't affect you in the long run, but just kind of going into more of the cardiac metabolism. Then seeing if this medication could then be used in Alzheimer's or other disease treatments, since it's already used for cardiovascular and diabetes problems. So a lot of ARBs are also used in other disease like medication and can be helped for that. So why not just kind of see, hey, look, if we already put this drug on the market, can it be used for something else? And the last part is the references. And so these are our references. And in the meantime, at the same time, thank you for watching. And I hope you guys enjoyed the presentation on Aprovel or Irbesartan.